All right, so it's recording. All right, so we're still doing random matrix theory. Random matrix theory covers a lot of things. And so the goal is to determine the correct statistic to study. The goal is to figure out what's going on with eigenvalues of matrices. And that's going to be the key object of study today, but you can apply this to a lot of other different things. We're going to see remarkably similar behavior in different systems, mostly in terms of the eigenvalues, but if you look at a bunch of related things, you will see that too. I will put additional material online if you want to read more about this, but I really want you to get a sense of how the other math classes you've taken have been important. Which math class do you think is the most important one for today? Linear algebra, excellent. All right, so the general formulation and most of my research can be summed up as follows. I have some system and I observe values at T1, T2, T3, and I want to discover what rules govern the spacings between the Ti. So, for example, it could be waiting for your number to be called at a bank or to get on an amusement park ride. Disney is outstanding at understanding waits between events and how lines move. When you go to a bank, how many lines are there at a bank? One. They all feed into 4 tellers. And this way is, if you had 4 lines with 4 tellers, you'd have the same average weight. But if you have one person who is high maintenance, they can knock out an entire line and give a very frustrating experience to a lot of people. So the variance in people's weights can go enormously if you have 4 lines. If you have 1 line feeding into 4 tellers, maybe the average variance will go up a little bit for a typical individual, but you are less likely to have a truly horrible experience. Why don't we do this in supermarkets? I think it's more than that.
There's a spot to put like one giant line of people.
Yeah, in a bank you could have one giant line. If you're going through the airport with security, you can have one giant line. If you try to imagine everybody with shopping carts, Christmas cheer, shoving each other, yes?
Well, they did a study also that it's really more efficient to take the person from the back of the line than to take the people from the front of the line. That people end up spacing their visits because the...
Oh, interesting. I've been at airports that actually operate like that, is you basically don't move until it's time for your flight and say, anybody who's on this flight, come to the front of the line. In which case, there's no incentive to get there early and get through security. So here are a couple of things we can look at. Energy levels between heavy nuclei. How many people have taken physics? Okay, so in physics, we don't understand that much, beyond hydrogen. So when you get to something like uranium, it's going to be very complicated. We're going to mostly study eigenvalues of matrices. There's some connections to L functions. I don't think we're going to have too much time to get into that today, but I want to give you a sense of where this goes and what kind of research I do, what I've done with a lot of Williams students over the years. We're going to be doing a lot of stuff like this in small this summer, and so if you're interested, please talk to me. Okay, so there are often 3 steps in terms of trying to decide what's going on. The first is to determine the correct scale for the events. So this is very similar when we were proving the central limit theorem. We standardized our variables. We subtracted off the mean, we divided by the standard deviation, and we got some nice universal random variable that had mean 0, variance 1. And that would then converge to the standard normal. The next is we want some kind of explicit formula which relates what we want to understand to what we're able to understand. One of my favorite quotes is, if all you have is a hammer, pretty soon every problem looks like a nail. The goal is, if you have a technique, a tool that's really good at X, you convert everything to X, and then you use your hammer. And then the last is we need some kind of averaging formulas to understand the things that come into play. So let me quickly review linear algebra. I know you're all experts. I know you've forgotten absolutely nothing from your linear algebra course, but this is just for completeness sake, shall we say. So we'll say some number z is a complex number if we can write it as x plus iy, where I is the square root of -1. The complex conjugate z bar is x minus iy. And we'll often write h. H means the complex conjugate transpose. So if you have a column vector, the transpose takes a column vector and makes it a row, I guess I'd go this way, makes it a row vector. The conjugate replaces every complex number by its complex conjugate. And so the h does both. Well, if I have just a number, it's a 1-by-1 column vector, it's a 1-by-1 row vector. That doesn't really change. Eigenvalue, eigenvector. So if you have a non-zero vector v and a complex number lambda, it's an eigenvector if AV is lambda v. So in general, when you apply a matrix to a vector, it's going to change both the direction and the magnitude. If it only changes the magnitude, it's called an eigenvalue eigenvector pair. These are extremely useful in understanding what's going on. I think we talked a little bit about trying to understand ellipses. If they're not aligned with the coordinate axes, you can rotate things. Essentially, the way you should view an operator in linear algebra is it's a transformation. Well, these are just big words. If you actually want to roll up your sleeves and do a computation, you want to write down the matrix. You want to give the matrix values. To give a matrix values, you have to choose a coordinate system. And that's why in different coordinate systems, the same operator will look very different. The whole point of eigenvalues, eigenvectors, is to look at a convenient coordinate system where the matrix is very simple, ideally diagonal. You can find the eigenvalues of the matrix by calculating the determinant of A minus lambda I equals 0. And if you just take this equation, if you subtract lambda I from both sides, you get the 0 vector. Then that means the matrix A minus lambda I acting on V sends it to 0. So you're finding something in the null space of this. If you feel that this is the way that you should calculate eigenvalues, you need help. That's the kindest way. And you can maybe blame your professor, but you would never do this in the real world. Your matrices will be 100 by 100. This would mean you would have a nightmare of a polynomial to evaluate, and you would have an enormous difficulty with numerical accuracy if you tried to do this. There's a lot of very interesting questions about how would you calculate something like this. Different types of matrices that are important. Real symmetric matrix, you equal your transpose. And typically here it's going to be real numbers. Your Hermitian, if you equal your complex conjugate transpose. So you take the transpose and then you take the complex conjugate of each entry. This implies that the diagonal entries of a Hermitian matrix must be real because they have to equal themselves. The length of a vector is just the dot product. And so the dot product of two vectors v dot w is actually vhw. You take the complex conjugate transpose. Okay, any questions on eigenvalue review 1? Moving on to, not surprisingly, eigenvalue review 2. So if A is real, then it implies the eigenvalues are real. So here's the quick proof. So AV equals lambda V. So I look at VH that's VHAV because AH is A. If the matrix is real, its complex conjugate transposes itself. Well, we do the main technique we've done all semester. We group things. One way is I group these two elements together. And when you take the transpose of a product is the product of the transposes in reverse order. So this over here becomes AV complex conjugate transpose with V, and this is VH with AV. When I apply A to V, I get lambda. When I apply A to V, I get lambda. Now I dropped the V over here, I apologize. I now pull the lambda outside. Since I'm taking its complex conjugate transpose, this becomes lambda bar. And so now I get lambda bar times the length of V squared is lambda times the length of V squared. Well, since the length of V is not 0, the only way this can be true is if lambda is equal to lambda bar, so the eigenvalues are real. This is extremely important from a physics perspective in that we can talk about these lambdas as maybe the energy levels of the system. And we can talk about spacings between eigenvalues. It's extremely important to have operators whose eigenvalues are real. So if A is complex Hermitian, it turns out this whole proof follows identically. I never used the fact that A was real. If you try to use V transpose A transpose, then you could potentially have problems. Because if your vector has complex coefficients, V transpose V can be 0 without the vector being 0. Look at 1i dotted with 1i. Okay, the other thing that this shows is that if A is real symmetric, not only are the eigenvalues real, but the eigenvectors are real. Oops. The last one, orthogonal matrix means Q transpose Q is Q, Q transpose is the identity. What this means is each row or each column has length 1, and the rows are mutually perpendicular, the columns are mutually perpendicular. These are a nice orthogonal change of variables. These are very good ones to do. So the big theorem from linear algebra is the spectral theorem. If you have a real symmetric or complex Hermitian matrix, you can diagonalize. If you can spell well, you can even use the correct then. And you can write A as Q transpose lambda Q. This is what we were doing when we were looking at ellipses. And what this is saying is that this operator is really the same as this diagonal operator if you do this orthogonal change of coordinates. And what you can do is you can then study the nice diagonal matrix and then you can convert backwards. It's the eigenvalues that are the most important things, not the coordinate system. I cannot prove to you that the universe does not care about which way I orient my fingers, but I'm pretty sure the universe does not care how I orient my fingers. That's what the Q is doing. The proof is trivial if the eigenvalues are distinct. So if the eigenvalues are distinct, you can choose, each eigenvalue has to have an eigenvector, choose the eigenvectors to have length 1, and it turns out they're all mutually perpendicular. And you just do the same calculation as before. Anything that you do more than once is no longer a trick, it's a technique. V1 transpose A transpose V2 is V1 transpose A V2. We group them as before, and now in this case I get a lambda 1, in this case I get a lambda 2. Well, if lambda 1 doesn't equal lambda 2, the only way this can be true is if V1 is perpendicular to V2 and their dot product vanishes. So you would get mutually perpendicular directions, and those become your Q. That gives you your matrix. And now if you apply the vector, well, it might be Q transpose. I think I've got things backwards, but all right. So this is the quick linear algebra review of what we're going to be needing. All right, so classical random matrix theory, this is some of the students I've worked with over the years. You may recognize one of the names, though no longer as a student. Okay, so classical mechanics. Okay, three-body problem is intractable. What that means is if I give you 3 point masses under gravity and no other forces in the universe, we cannot write down in closed form where the 3 bodies will be as time evolves. This is one of the classical things leading to chaos. We just can't do this. We can sometimes bound the orbits and say, oh, they'll be somewhere in this blob of space. But to know exactly where they are, we can't do that with 3 bodies. So now imagine uranium with over 200 protons and neutrons. So I actually started off doing experimental nuclear physics when I was an undergraduate, working with a lot of this data. My mentor, Professor Firk, was sick and tired of how few data points you had in nuclear physics. You see the same behavior in looking at the Riemann Zeta functions and primes in number theory. And so you got very interested in stuff like that. So you get some information from shooting high-energy neutrons into the nucleus and seeing what comes out. One of the best quotes I heard about this is, to put this in perspective as to the challenge nuclear physicists have, imagine you want to understand how a grandfather clock works. And the way you're going to do it is you're going to take 2 grandfather clocks and you're going to accelerate them to 0.99 times the speed of light and then smash them together, I apologize if you were sleeping, and see all the cogs and wheels and things that fly out. And from all the stuff that flies out, you're going to then deduce how a grandfather clock works. This is essentially how nuclear physics works. And you have to deal with issues like this. You can't shoot an arbitrary neutron in. You can only shoot neutrons of specific energy bands. And you have to then deduce what can you say given this limited information. So it's a real challenge. It turns out in quantum mechanics, we can basically describe physics as the following eigenvalue equation. You have some matrix H, the Hamiltonian of the system, and you have some eigenfunctions C of n, and E of n are the energy eigenvalues. So physics is reduced to linear algebra. You've all taken linear algebra. There are only 2 things about H that make this a little bit different than the linear algebra you've done. The first is H is infinite by infinite. And I'm assuming you've not done anything with infinite-sized matrices. The second is we don't know any of the entries of H. So I need you to diagonalize an infinite by infinite matrix, and I can't give you any of the entries. Good luck. Not going to happen. So Wigner's great insight, and this led to random matrix theory coming into physics, was to draw inspiration from statistical mechanics. So imagine you want to calculate some macroscopic quantity like pressure. The way you calculate it is you say, let's look at a small amount of time and let's see how many molecules hit my wall in that amount of time. For simplicity, I'll assume molecules only move left and right. They all move at the same speed. Now, to actually do this calculation, I would need to know where every single molecule is in this room and how they're moving. Anybody know roughly how many molecules are in this room? Google is way too high. Wait, what's a Google? Google is under the 100, right? Yeah, way too high. What?
100 moles.
Yeah, about 100 mole is a reasonable number. A mole is about 10 to the 23. So if you said around 10 to the 25, order of magnitude, that's around how many things you have. We are not going to compute with 10 to the 25 objects. So Wigner's great insight was basically to say, screw that, and look at a system average. For each configuration of the molecules, calculate what the pressure would be, average over all configurations, and then say the specific state you're looking at will be well approximated by the system average. Does this remind you of anything? Which thing in probability? I'm sorry? Yes, central limit theorem is basically pray that a central limit theorem emerges and describe what's going on. And it turns out that that's the case, that most systems are close. Is it possible that all the air molecules in the room could go to the front? Yes. This would be extremely bad. We would lose a lot of future donors to Williams College. How likely is it? Well, if there are n molecules in the room, how many molecules do you expect in the front relative, and how many in the back, roughly? 1/2, so n halves in each. What do you expect the scale of fluctuations to be? Square root of n. And if n is huge, on the order of 10 to the 25, square root of n, 10 to the 12th, 10 to the 13th, divided by 10 to the 25, we can't even notice this percent difference. So the fluctuations will not be noticeable. And this is one of the reasons why I'm pretty convinced nobody will asphyxiate and die in the course of this lecture. Do not try to prove me wrong. All right, let me quickly review random matrix ensembles. So here's a real symmetric matrix, so Aij equals Aji. And what makes it a random matrix is I'm going to choose a probability distribution P, and maybe I'll choose it to have mean 0, variance 1, finite moments, and I'll choose my elements randomly according to this distribution. And then the probability of choosing my matrix is just going to be the product of the probabilities. To unwind this a little bit more, the probability I have a matrix A where the ijth entry is in the interval alpha ij, beta ij, is I just integrate my probability from alpha ij to beta ij, and I do this for all the independent random variables. So the independent random variables will be the main diagonal and everything above. Or if you want to go against everybody else, the main diagonal and everything below. Doesn't really matter which way you do it. We typically like to work above, but it doesn't matter. So this is the random matrix ensemble. Now, the first question, of course, is, well, which P do we use? If you had to guess a P, what P would you guess? I'm sorry? A normal. It turns out that if you assume that the probability of choosing a matrix is unchanged if you do an orthogonal change of variables, it forces P to essentially be a Gaussian. And it's a nice differential equations calculation to do this, which is really fortuitous because up until about 5-10 years ago, that was the only matrix we could work with in general, is matrices coming from the Gaussian. The other ones we just could not do the calculations for all quantities. For some quantities we could do, such as the semicircle law, which we'll get to very soon. But the general spacings between eigenvalues we could only do if it was a Gaussian, which happens to be the most physically natural one. Do we care about the coordinates we've chosen when we represent the matrix? No. We care about the eigenvalues. That's the true quantity. Those are the energy levels. So the fact that the matrix eigenvalues are what matters, we want the probability of the matrix, if we do physics, to be unchanged under orthogonal conjugation. And that does lead to a Gaussian. But you can do the theory for different P's. You can also put in other structures here. This is a very weak structure that it's real symmetric. Why are we asserting the matrix is real symmetric? We want the eigenvalues to be real. And that will model a lot of physical quantities. Okay, so we want to understand the eigenvalues of A, given that we know the entries of the matrix. Does anybody know any results connecting the entries of a matrix to the eigenvalues? It's old linear algebra now. Yes?
The sum of diagonals.
Excellent. The sum of the diagonal, the trace of the matrix, is the sum of the eigenvalues. And you can generalize this. The trace of A squared is the sum of the squares of the eigenvalues. The trace of A cubed is the sum of the cubes of the eigenvalues. This should remind you a lot of moments. And we did a lot about how we could use moments to understand probability distributions. We can do the same here. If we can understand the trace of powers of A, we can get moments of the eigenvalues. And if we know the moments of the eigenvalues, we know the distribution of the eigenvalues. And it makes sense that we can get things about the trace of A to a power because it's the elements of A that we're choosing randomly. Okay, so what we're going to do is I'm going to introduce some notation. Delta is a probability, density may not be the right word, it's basically a unit mass. All of the mass is concentrated at the point x0. And so if we integrate a function f of x against the delta measure, we just get the value of the function at x naught. Think of it as the density is 0, 0, 0, 0, 0, 0 until you get to your point where the density goes up to plus infinity. Okay? So all of the mass is carried at one point. To each matrix A, I can associate a probability measure as follows. There are n eigenvalues, so I give each eigenvalue a mass of 1 over n. And I put a mass at the normalized eigenvalues. I'm dividing each eigenvalue by 2 square roots of n. Which do you think is the really important number, the 2 or the square root of n? The square root of n. That's what tells me how things change as n grows. The 2 is so I can use the word circle and not the word ellipse later today. We talked earlier about the change of variables to make circles into ellipses or ellipses into circles. The 2 is not a big deal. The big deal is the square root of n. That's the one that really matters. And so if we integrate this probability measure from a to b, well, every time x goes through one of these normalized eigenvalues, we get 1 over n, and otherwise we get 0. So this is going to count how many normalized eigenvalues do I have between a and b. And it just counts all of them and divides by the n. That's the 1 over n here. If I wanted to calculate the kth moment, I would just integrate x to the k times this. And the only thing that would change is I would now have the eigenvalue of a to the kth power divided by 2 root n to the kth power. So when you do the algebra, you get the trace of a to the k over this. We want to understand the eigenvalues. This stuff over here, this is the kth moment of the eigenvalue. Wonderful, that's exactly what we want to understand. And it relates the kth moment to the trace of a to the k. So one of the dangers when you take introductory math courses is you have no idea why you're doing it other than it's in the syllabus. And so you prove this result, the trace of the matrix is the sum of the eigenvalues. You should be thinking, who gives a... If you don't have that thought, I'm shocked. It doesn't seem like a very useful result. Now you can begin to see why, in my mind, this is one of the most important results in linear algebra. It allows you to get your hand on the eigenvalues through something you know. All right, so the big result is Wigner's semicircle law. If you have n by n real symmetric matrices, entries independent identically distributed from some nice probability distribution, mean 0, variance 1, and other moments finite, then for almost all matrices, as n goes to infinity, the normalized measures are converging to the density of a semicircle. And so this was Wigner's great insight, is rather than studying an infinite matrix where we have no idea what the entries are, look at a very large n by n matrix, choose the entries at random, calculate the eigenvalues. Then choose another set of matrices, calculate the eigenvalues. Choose another matrix, calculate the eigenvalues. And average. And the idea is a typical matrix will be close to the system average. Is it possible I could choose the matrix that's all ones? Yes, but it's unlikely. Most events will be close to the system average. Okay. So I'm going to give you a sketch of the proof and show you what goes into something like this. So as we talked about before, we have the eigenvalue trace lemma. The trace of a to the k is the sum of the eigenvalues to the kth power. If you've only done the trace of a as the sum of the eigenvalues to the k, this is a really good thing to try to prove. I'm keeping the homework minimal. This is a great homework problem to try to do. And I'll make that an extra credit problem. The trace of a to the k turns out to be a really nice expression in terms of the matrix elements. It's this nice cycle. A sub I1, I2, I2, I3, I3, I4, all the way up to In, I1. Just cycles around. All right, so now let me start going through how we use this. So the first thing is trying to find the correct scale to study something. So I said you divide by the square root of n. Here's a place where the central limit theorem comes into play. The trace of a squared is the sum of the eigenvalues squared. By the central limit theorem, well, the trace of a squared is the sum of the eigenvalues, is the sum of aij, aji. Well, it's real symmetric, so this is the sum of aij squared. These are all independent random variables. Well, okay, ij is the same as ji, so I have a double counting, but what's the expected value of a sum? Sum of the expected value. Because the aij's have mean 0, variance 1, the expected value of aij squared is just the variance of aij, because the mean is 0. That's just 1. So we expect this sum to be of size n squared. What would you expect the variance of this sum to be of size? Variance should be of size just n. You expect square root cancellation. But of course, you've got to be a little bit careful because these are all positive numbers, but maybe the fluctuation should be on the order of n, and these should be with high probability of size n squared. Well, if the sum of the eigenvalues squared is of size n squared, if I just formally say n times the average square is n squared, so the average of these is looking like square root of n. I'm playing a little bit by moving square roots inside averaging. I have a degree in physics, I'm allowed to do this. But ballpark, this is giving us intuition that the correct scale is square root of n. And that's how we should normalize the eigenvalues so that in the limit as n goes to infinity, we will actually see something. When we did the normal central limit theorem, we subtracted the mean, we divided by sigma root n, and that had a nice limit as n went to infinity. This was all about finding the right scale to study. So again, one of the whole purposes of these lectures is to review everything we've done. I'm happy to hold extra office hours before the final, but that's essentially what these 2 weeks are. It's reviewing what we've done with a mind on applications. So recall the kth moment is the trace of a to the k. So the average kth moment is we just put in our probability density and we just integrate. This is a polynomial, so we just have to do these integrals. And so what you need to do is you need to show that the average kth moment converges to the kth moment of the semicircle, and you need to somehow control the variance. So imagine I have a sequence that half the time is 0 and half the time is 2. On average, it's 1. But it would never be close to 1. Right? So even though the average is 1, no element of my system is ever close to the system average. So I need to control the variance. If the average is correct and the variance is going to 0, then everything is going to be, almost everything will be close. And that's why you have to control the variance as well. So let's calculate the second moment. So if we substitute, we get a ji squared times all these different probabilities. Well, there's one integral that involves an a, and then all the other integrals, what do these integrals equal? 1. We're integrating a probability distribution. The integral of a probability distribution is just 1. This integral turns out to be 1 as well because it's the variance, and we've chosen the variance to be 1. This is an extremely misleading slide. It makes it look like this is easy. It's actually a lot of very involved combinatorics. If you know what the Catalan numbers are, they come into play. The kth moment, we have something like this. Well, we assumed that our moments, that our random variables have mean 0. If there was ever an a that was unmatched, when you integrate it, it would be 0. So all the a's have to be matched in at least pairs. It turns out if you ever have a triple match, then you're going to have a lower order because of how many n's we're dividing by. And a triple match, when you do the combinatorics, it turns out it gives you a lower order contribution and it doesn't matter in the limit. So you have to have everything matched in pairs. So first of all, it tells us that k must be what kind of number if things must be matched in pairs? Even. So let's say k equals 2m. How many ways are there to match 2m objects in pairs? 2m minus 1 double factorial. You should be smiling. Where have we seen 2m minus 1 double factorial before? The moments of a Gaussian. Lurking in the background is a Gaussian. If every matching contributed equally, you would get a Gaussian. We're not getting a Gaussian, we're getting a semicircle. The semicircle has bounded support. When you go beyond minus 1, 1, there's no probability. What this means is some of these matchings either contribute a lot less or contribute 0. And that's where things get very interesting as to which matchings contribute. So I'm going to just show you 2 numerical examples. I chose a Gaussian, 500 matrices, 400 by 400. If you have really good vision, there's a red line. Does it look like it's given by the semicircle? In the interest of time, I'm not going to show you uniform, Poisson, exponential. Well, exponential would be bad. And some of these you'd have to normalize to make symmetric. They all obey the Wigner's semicircle law. What would be a really good example to see how robust the semicircle law is? Cauchy. Okay. All right. Hopefully you can see it is not a semicircle. What these blips are at the end is looking at all the eigenvalues this large or larger. The Cauchy violates the assumption and has markedly different behavior. But it turns out that they have the same behavior for something else. This was counting how many normalized eigenvalues we have. We could instead count how what's the spacing between eigenvalues appropriately normalized? And so there's this wonderful thing called the GOE conjecture that it doesn't really matter what p you choose, the spacing between events appropriately scaled is universal, and it's approximately x e to the minus x squared. Does this look familiar? Where have we seen this? We saw it on Monday. It's the Weibel. We saw it on an exam. It's the Weibel distribution. This is where I had the idea to use the Weibels to model things in baseball, because I knew about the Weibels from random matrix theory. This is going back to, if you have a hammer, use it. That's why I thought to use Weibels. I know this distribution. Only recently did we know these results for the Gaussian, but now we know it for almost all p. So this is the uniform distribution. This is looking at spacings. The solid line is the theory, essentially. The histogram is what we observe. And this is 300 by 300 matrices. Pretty good fit. What should we test now to see how robust? Cauchy. Not as good of a fit. But we're only doing Cauchy matrices that are 100 by 100, and here we're doing 300 by 300. We're comparing apples and oranges. We need to know rate of convergence. What should we do? Yeah, do 300 by 300 Cauchy. And you see the GOE law coming into play. You can look at random graphs. And so a graph is a bunch of vertices and edges connecting them. And you can form an adjacency matrix. And each element tells you how many edges you have connecting the vertex. And you can calculate the eigenvalues. And these are real symmetric matrices. And it turns out that there's a density of eigenvalues for d regular graphs. D regular just means each vertex has exactly d neighbors. If you look at this when d equals 3, this does not look like a semicircle. But as d goes to infinity, this actually converges to a semicircle density appropriately normalized. So you need to normalize, you pull out a square root of d from this, so you divide this by d, you divide x by d, it becomes a semicircle. Looking at d equals 6, you can begin to see the semicircle emerging. And if you look at the spacings between adjacent eigenvalues of d regular graphs, you see the GOE law again. Remarkable universality. What I want to do now is talk about some very special families of matrices. I want to talk first about Toeplitz matrices. So I started looking at these about a decade ago. And so a Toeplitz matrix, you're constant along diagonals. So it's B0 along the main diagonal, B1 above, B2, B minus 1. If it's real symmetric, what's the relationship between B1 and B minus 1? They have to be equal. So you can calculate what's going on, and you can calculate enclosed, you can calculate a lot of things about the eigenvalues. So we have our eigenvalue density measures. The kth moment is the trace of a to the k. We want to calculate the average kth moment. So all that matters is which diagonal you're on. And so we want to know, we match things in pairs, which matchings contribute. So I'm not going to go through all the different details. There are 2k minus 1 double factorial ways to match. For each thing over here, when two things are matched, there's two different ways they can be matched. They can be on the same diagonal, and that's going to be with a plus sign, or they can be on opposite diagonals with a minus sign. It turns out by doing some basic combinatorics, the only terms that survive is when they're on opposite diagonals. And you get very quickly a bound of the Gaussian moments for the moments here. If you actually start looking at the combinatorics, there are three possibilities of how to match things in pairs. Adjacent matchings, opposite matchings, or just the adjacent matching going the other way. It turns out the adjacent matchings contribute fully, and this contributes reduced. I'm not going to go into all the details. If you want, the papers are very accessible. Happy to chat about this. This is all work done with undergraduates. And so you just go through, you do the calculations. This way it's up here. And you get the following. The fourth moment is 2 2/3. The Gaussian's fourth moment is 3. When you look at this figure, what do you see? A normal. We looked at this, we saw a normal, we conjectured it was normal. We talked to some colleagues, they gave us heuristics as to why it was a normal. Turns out there was another group working on this problem at the same time elsewhere in the country. They also thought it was a normal. It's very natural when you look at this, oh yeah, it's experimental error. You've got to be very careful about data. Data can be misleading. And it's not just that I'm incompetent, there was another group, they made the same mistake. We all thought it was normal. Okay, And so we proved that the limiting spectral measure converges in probability, this is one of our many types of convergence, to a unique measure of unbounded support, so it's not confined, and it's not the Gaussian. We actually have a lot of information about how rapidly the moments grow. They grow so slowly that if you divide them by the moments of the Gaussian, that ratio tends to 0. But they do grow fast enough to give unbounded support. The behavior between normalized eigenvalues is very different than the behavior in the real symmetric matrix or in d-regular graphs. It's Poissonian, much more like the behavior of primes. And it's a big question as to why do different systems. The structure of the matrix ensemble has a huge impact on what's going on. I'm not going to go into here, but it wasn't a normal, but it looked so close to normal. The feeling was there must be some defect. We're looking at the wrong quantity. And so in our paper, I conjectured that if you made the first row a palindrome, that would fix the problem. So a palindrome is ABBA, great musical band, we can use them again. A Man, a Plan, a Canal, Panama. So now we have B1 over here, and we have a little bit of extra B1 over here. We have B2 over here, we have a little bit of extra B2. The point now is each band has essentially the same number of elements. Before, when it was not a palindrome, the diagonals further out had fewer elements. It turns out putting this in balances all the problems we had, and you actually get a Gaussian. And so I'm not going to go through the details, but you get a Gaussian. You actually get a new central limit theorem, which my students and I proved. You can look at highly palindromic matrices, where you can make the first row multiple palindromes and see what goes on. There's a lot of work that we've done here. I'm not going to go through that. I want to end with block circulant matrices. So for me, I always want to have ways of generalizing, of having something fit inside a family and see new behavior, have a dial I can turn. So what I'm doing now is on this diagonal, rather than having every element the same, I'm going to have it periodic with period 2. If it was periodic with period 1, it's what we've already studied. If it's periodic with period essentially n, then it's basically my real symmetric matrix. I'm sorry, if it's, yes, because then I could have n different elements. So this gives me a way to interpolate between the Toeplitz ensemble, which is very structured, and the unstructured real symmetric matrices. And so, again, you want to calculate, as before, the moments. Things have to be matched in pairs, and you get contributions based on how things are matched. I'm pretty sure no one here has taken a topology class. Has anyone taken topology? So you could draw little figures, and you can identify edges. And you glue them together so that the arrows are pointing in the same direction. And you have two ways of gluing them, of putting the edges. They can be the same way, they can be opposite ways. If you want to play Pac-Man, if you go off one side, you come in on the other. You glue them together like this, and if you can also go off the top and come in the bottom, you would glue it like that, and you would get a donut. So the way to view a donut is you have a square where the two parallel sides are both paired. These two both go up, these two both go left, so when you glue it together, you get a donut. If you were to twist one of them, you start getting different figures. So I talked earlier, without going into details, that you had two choices. You could be on the same diagonal and have plus signs, or opposite diagonals be minus. It turns out the only ones that matter are when you have when you have the minus signs. That means these are both pointing in directions like this, so you can glue them together. So things here where the arrows are pointing in opposite directions, those don't contribute at all. There's a lot of topology that starts to emerge in problems like this. This gives you basically a torus. And the contribution from such a pairing is m to the minus 2g. G is the genus, it's the number of holes of your object, and m is the period. So now the even moments, we have this beautiful formula. Epsilon g of k is the number of pairings of edges of a 2k gon that give rise to a genus G object. Does this look like anything you've seen before? And the hint is the words are on the slide. Generating functions. Instead of using the variable x, we're using the variable m. And here are my coefficients. I would love to take this local data and get a nice global object and deduce things. It turns out Harari and Zagier did just that. And they were able to get a nice closed form expression for this in terms of a beautiful polynomial. Think back to the Fibonacci's. Think back to Binet's formula. How if we have a closed form for the generating function, there's a lot we can do. And we actually get a very nice expression for the moments. We have the 2k minus 1 double factorial, and we have these coefficients. These coefficients are less than 1 and decrease us from the Gaussian. So if these were all 1, we would get a Gaussian. The further they are from 1, the closer they are to 0, the more we pull us towards the semicircle. Characteristic functions. This is very similar to, we did moment generating functions. The only difference of a characteristic function is instead of using t, we use I times t. So we calculate just exactly as you would before. The reason I don't have any of the odd values is all the odd moments are 0, so I can ignore them. So I calculate the generating function. Or here, because I'm using I, the characteristic function. It turns out that I can write this sum as a contour integral. This is where complex analysis comes into play. And I integrate over a circle of radius 2. And there are ways to pull these numbers out. And complex analysis allows us to calculate stuff like this. And we get this beautiful closed form expression. And now we go from an infinite sum to a finite sum. Notice what's sitting outside over here. What is this? What is this over here? Clock is ticking. We're running out of time. It's a normal. And then here is something which is shrinking the power, the size of the normal. And so we actually get a closed form expression. We then take the inverse Fourier transform to go from the characteristic function to the actual density. And we have an explicit formula for the density. It's a normal times this dampening factor. And we can see, we can analyze what happens as m goes to infinity. As m goes to infinity, it starts to converge to being a, I'm blanking on the word. It starts to be a semicircle. So let's look at pictures. This is the case of f equals 1, of m equals 1. Looks fairly normal. And now what we're going to do is we're only looking at 100 circular matrices of size 400 by 400. This is not a large numerical simulation, and this is deliberate. We can see the bump very clearly with our data. And our theoretical prediction is dead on here. Now looking at 3-block matrices, 4-block, 5-block, and you can see going up and down is mirroring the behavior extremely well. Already at 20, it's very close to the semicircle. The support is still infinite, but it's decayed so much by this point that it's essentially done. And just plotting them all together. So we've got about 2 minutes left, so I'm going to skip all the weighted symmetric stuff. Hopefully you can pause or just look at the slides. And I want to briefly talk about L functions. So the Riemann Zeta function is one of the most important functions in all mathematics. So it's the sum of 1 over n to the s, where n ranges over all integers. It's the same as the product over all primes of 1 minus 1 over p to the s inverse. When you see this, you should be thinking geometric series, where the ratio is 1 over p to the s. And if you expand things out using unique factorization, these two are equal. Somebody very quickly, because we're running out of time, the next integer after 2015.
What?
Next integer after 2015. Next one. Okay, so we can understand the distribution of integers very well. The idea is to pass from that to knowledge of the primes. Okay, and so by unique factorization, we expand everything out. There's a lot of connections between the zeta function and counting primes. The Riemann hypothesis basically says if you continue this so that it's defined for all complex numbers s, the zeros, the location of the zeros of this are related to counting the primes and the errors. I'm not going to go through a lot of these proofs. If people want to, we can talk about this later. But the remarkable observation is the spacings between zeros of this Riemann zeta function behave like the spacings between eigenvalues of complex Hermitian matrices. This was one of the most shocking connections made in mathematical physics in the 1970s by Montgomery and Dyson. That the same mathematics that described high-energy nuclear physics, uranium, is describing the Riemann zeta function in primes. And so I'm going to skip a lot of the stuff on elliptic curves. It turns out that there's an analog of the eigenvalue trace lemma. If we do contour integration, if we integrate the logarithmic derivative, we can actually get a relationship between the zeros of the Riemann zeta function and basically the coefficients. And it's going to be like a Fourier transform. You can do this more generally. And I'm going to just end with, it seems like it's very similar to the central limit theorem. the same stuff is coming in. The universal convergence is coming from the coefficients, that all that really matters is the first and the second moments of these coefficients, just like the central limit theorem. The higher moments only affect the rate of convergence. In terms of being able to do calculations and prove theorems in number theory, in the stuff over here, we can only prove results like this for very special test functions. And there's something called the support of the test function. It has to live between two finite numbers. We would love to be able to take arbitrary support. If we could understand everything. That would be equivalent to taking taking neutrons of arbitrary energy, which we can't do in physics. So there's a lot of connections between them. What I hope you got out of this is that the math you are doing is already enough. If you want to do small this sum, if you want to work on questions like this, you've got enough background. You are already at the point where you can do cutting-edge research in number theory, random matrix theory, mathematical physics. There's a lot of great ensembles to look at. You've got the tools. The stuff you've been doing in linear algebra is useful. All right, time to go. So.